So this is the last section, Taylor series and applications. So far we've kind of talked about Taylor polynomials, and now what we're going to do is that we're going to extend this to infinity. So basically, as you tend to have many, many different polynomials, an nth degree polynomial, or keep going, that's going to be approximate the function exactly. So here is when it's centered at 0. So notice that you're just plugging in 0 and then you don't have anything next to the x. Here is when it's centered at some number a. So here you have this a and then you have this a over here. But the formulas are basically the same. Then all you got to do is just plug in 0, 1, 2, all the way until you get to wherever you want to go. Okay, now one thing that we kind of know is that if I were to find the Taylor series of e to the x, it'll just be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. So if I were to do this many, many different times, you'll just have all of this guy. And actually, this has a closed form. It's n goes from 0 to infinity of x to the n over n factorial. Now, you don't need to know this, but I will be giving you these guys to be able to find new Taylor series. So for example, let's say I want to find the Taylor series. So Taylor, whoops, not Taylor's, Taylor series for g of x equals e to the negative x cubed. Okay, well, this one is not as bad because one thing that you can do is we know what the Taylor series of e to the x is. So the Taylor series of e to the x is just what I just wrote down. 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and I just keep going. So if I wanted to figure out what e to the negative x is, e to the negative x cubed, all I have to do is plug in this thing into the x's. That's all I gotta do. So this guy is just going to be 1, so there's no x there, so that's still going to be 1. Then I'm going to plug in negative x cubed in there over 1 factorial. Then I'm going to plug in negative x cubed in there. Remember that there's a squared there. Then negative x cubed here. There's a cube there. And then negative x cubed there, 4 over 4 factorial. So basically, I'm using one of the known Taylor series to be able to figure out the other ones. Okay, this looks really ugly. So x cubed to the cubed. Okay, so now all I gotta do is just clean it up a little bit. So it'll be 1 plus negative x cubed over 1 factorial. Squaring this 1 is gonna give me a positive 1. And then I'm gonna have x to the power of 6 over 2 factorial. Cubing this 3 is gonna give me a negative 1. It's negative x to the power of 9 over 3 factorial. So you can see that this guy's going to be negative. And then taking the 4th of this is going to be a positive 1, so it's x to the power of 12 over 4 factorial. Plus, and then continues on. Okay, so basically this is going to be the Taylor series centered at 0 for e to the negative x cubed. So this is really good because then what we don't have to do is take multiple derivatives of this. Okay, of course you can do it the long way. You can take f of x starting off at e to the negative x cubed and then take the derivatives of this. But the thing is that taking the derivative of something like this is going to be really nasty. So sometimes it's easier to just use a Taylor series that we already know to be able to kind of have all of this write out all of this Taylor series. Now, if I only give you this guy, then we can still do it, and I'll show you how to do it. Let's say we didn't have this, but we have this, we can also just do it very easily. So let me give you another example. So let's say we want to find this. So given the Taylor series of cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th, whoops, over 6 factorial, and then it keeps going. And this is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. Okay, so let's say we had that. So we want to do two different things. So part A, find the Taylor series. Okay, still centered at 0 for cosine of x squared using the known series of cosine of x. Okay, so that's where we want to start off first. So very simple. All we got to do is just plug in x squared. So we're going to write cosine of x squared. And we're just going to plug in x squared wherever I see an x. And I'm also going to plug it in here as well. I'm going to have 1 minus x squared, and then squared over 2 factorial, plus x squared to the 4th over 4 factorial, minus x squared to the 6th over 6 factorial. And that equals to the sum from n goes from 0 to infinity, negative 1 to the n, x squared over 2 to the n over 2n factorial. Okay, so now let me clean this up, and you'll see why I'm actually going to write it in here as well. So I'm going to have 1 minus x to the 4th over 2 factorial, plus x to the 8th over 4 factorial, minus x to the 12th over 6 factorial. And this is going to be equal to the sum from n goes from 0 to infinity. This guy is just going to be x to the 4n over 2n factorial. Okay, so this is basically what it is. Now, if you are using WebAssign, usually it'll tell you, oh, give me just 3 of them. So you'll do the first 3, or maybe it might want you to do the whole thing. Okay, but I'm also writing it like this because there's a part B that's going to make you use this second part. And that's basically how calculators work. So this is going to be the part B. Okay, so use the Taylor series of cosine of x squared to estimate the integral from 0 to 0.2 of cosine of x squared dx up to 2 terms. Okay? So there's many different ways you can do this. I'm going to go ahead and just use this guy right here. Okay. Now notice that this integral from 0 to 0.2 cosine of x squared, you can't solve it using any methods. Not use substitution, not integration by parts, nothing. Okay. You have to either use some sort of trapezoid rule, Simpson's rule, or something. So what we're going to do, we're going to use Taylor series. And this is how we're going to do it. Well, we know that this guy is equal to the cosine of x squared. So what we're going to do is plug that guy in there. So I'm going to have, let me use a different color. We're going to have the integral from 0 to 0.2 of the sum from n goes from 0 to infinity of negative 1 to the n, x to the 4n, over 2n factorial dx. And now what we're going to do, we're going to take out everything that doesn't have an x. Okay, so first of all, the sum doesn't have an x. The negative 1 to the n doesn't have an x. This has an x, so it's going to stay. You have a 2n factorial, which doesn't have an x. So the only thing that's left over is the x to the 4n. That's the only thing that's left over. And now what you want to do is you want to take the antiderivative of this. Now this is super easy to take care of because this is really hard to take the antiderivative of, but we can do the antiderivative of this. So we first start off with the summation from n goes from 0 to infinity of negative 1 to the n over 2n factorial. And now this guy, well, I know the antiderivative of that. All we got to do is just add 1, x to the 4n plus 1 over 4n plus 1, evaluated from 0 to 0.2. Now, in order to do this, all we got to do is just plug in the 0.2 and then the 0. But the 0 is just going to go to 0, so we don't got to do that. So we're going to have the sum from n goes from 0 to infinity of negative 1 to the n, and a plug in 0.2 to the 4n plus 1 divided by 2n factorial, and then this 4n plus 1 is left on the outside. Okay? All right, so we're basically almost done because now all we have is a summation. So basically this summation is the integral of all of this stuff. Okay? This is kind of how your calculator does it. Your calculator can't do this, but it can sum up a whole bunch of numbers together. Okay, and that's kind of how your calculator is working. So what you're going to do, if we look at the problem, we only want it up to 2 terms. So we're going to do first the first term, which is n equals 0. And then we're going to do the second term, which is n equals 1. So first plugging in 0, negative 1 to the 0 power, 0.2. When I plug in 0, I'm just going to get a 1. Then 2 times 0 factorial. Then this is going to be a big fat 0 plus 1. And then I'm going to add this to negative 1 to the first power, 0.2. Then you plug in 1, that's 4 times 1 plus 1 gives me 5, divided by 2 times 1 factorial. Then that's going to give me another 5. Okay, so what is this going to give me? So this, on the top, I'm going to get 0.2. Then you have a 1 and a 1. That's just going to give me over 1. This is going to give me a negative 0.2 to the 5th power. This is going to be 2 factorial, which is just 2 times 5. So all we got to do is put this in our calculator. So let me get out my calculator. I'm going to put 0.2 over 1 plus, let me put this in fraction form. So negative 0.2 to the 5th power over 2 times 5, which gives me 10. And what I ended up getting is 0.199968. That's what I ended up getting. Okay, so basically, if I were to maybe put this in the calculator or somewhere else, this integral is going to be about this amount. Okay, which is actually really, really cool, and it shows you how calculators are programmed using Taylor series. Now we have a lot more different types of methods that are easier to kind of like program calculators. We use other different types of method, but this is one way that we can kind of see how the calculators work, and they're actually not doing all this integration.